In this video, we're going to look at the sp³ hybridization present in methane and ethane. Now, let's start with methane. So that's CH4. If I want to draw a dot structure for methane, I would start with carbon and its 4 valence electrons. And then we'd put hydrogen around that. Each hydrogen has 1 valence electron, so we go ahead and draw in our hydrogens with 1 valence electron. And that gives us the Lewis dot structure. Right? Usually you see it drawn like this, with carbon with its 4 bonds to hydrogen around it like that. And in methane, all of these bonds are equivalent in terms of things like bond length and energy. And so the 4 valence electrons that carbon brought to the table over here, let me go ahead and highlight those 4 valence electrons. Those should be equivalent. And if we look at the electron configuration for carbon, let's go ahead and do that right now. It's 1s2, so I go ahead and put in 2 electrons in the 1s orbital. 2s2, I go ahead and put in 2 electrons in the 2s orbital, and then 2p2. And so I'm assuming you already know your electron configuration, so it would look something like that. If we look at those 4 valence electrons on our orbital notation here, that would be these 4 electrons here, the valence electrons in the outer shell. And if we look at this, this implies that carbon would only form 2 bonds because I have these unpaired electrons right here, and everything's of different energies. And so what we see from the dot structure and experimentally doesn't quite match up with the electron configuration here. And so to explain this difference, Linus Pauling came up with the idea of hybridization. And so the first thing that he said was you could go ahead and take out one of these electrons in the 2s and promote it up to the p orbital here. So let me go ahead and show that. So we've moved one of the electrons up to the 2p orbital. So we're in the excited state now. And now we have the opportunity for carbon to form 4 bonds. However, those electrons are not of equivalent energy. And so Linus Pauling said, let's do something else here. Let's go ahead and promote the 2s orbital. All right, so we're going to take this s orbital and we're going to promote it in energy. And we're going to take these p orbitals and demote them in energy. So we're going to lower those p orbitals like that. So we have our p orbitals here. Right? And these had 1 electron in each of them. But we're going to hybridize them. So this is no longer going to be an s orbital. It's going to be an sp³ hybrid orbital. This is no longer going to be a p orbital. It's going to be an sp³ hybrid orbital. And same with these. Right? So the idea is you're taking some of the s character and some of the p character, and you're hybridizing them together into brand new orbitals. And since you're taking this from 1 s orbital and 3 p orbitals, right, we're doing this using 1 s orbital and 3 p orbitals, we call this sp³ hybridization. So this is sp³ hybridization. We create 4 new hybrid orbitals. And now we have what we're looking for, because now we have 4 unpaired electrons, right? So carbon can form 4 bonds now, and they're equal in energy. So that's the idea of hybridization. All right, let's think about the character or the shape of this new hybrid orbital. Well, we know that an s orbital is shaped like a sphere. Right, so we're taking one of those s orbitals here, so 1 s orbital, and we know that a p orbital is shaped like a dumbbell, right? So we're taking 3 of these p orbitals here, so 1 of these s orbitals and 3 of these p orbitals, and then we're going to hybridize them together. And when that happens, it turns out the shape of the new hybrid orbital you get has this large frontal lobe here like this, and then a smaller back lobe back here like this. So we're going to make 4 of these. Right, so once again, we have 4 sp³ hybrid orbitals, and each one of these hybrid orbitals is going to have an electron in it. Right, so we can see that each one of these sp³ hybrid orbitals has 1 electron in there like that. And so the final orbital, the final hybrid orbitals here contain 25% s character. Let me go ahead and write this down here. So 25% s character and 75% p character in this new hybrid orbital. Once again, that's because we started out with 1 s orbital and 3 p orbitals for our hybridization. All right, let's go back to methane, and let's go ahead and draw in a picture, because now we know that this carbon is sp³ hybridized. So let's go ahead and draw a picture of that hybridized carbon here. Right, so we're going to go ahead and draw in our carbon, and we know that it has 4 sp³ hybrid orbitals. And once again, when we draw the orbitals, we're going to ignore the smaller back lobe here so it doesn't confuse us. So we go ahead and draw in, here's one of our orbitals for carbon. So that's an sp3 hybrid orbital. Here's another sp3 hybrid orbital. Here's another one, and then finally a fourth one. All right, so let's go back up here to this picture. Right, because once again we need to show that each of these hybrid orbitals has one valence electron in it. So I can go ahead and put in my one valence electron, right, in each of my hybrid orbitals like that. So here's our valence electron. If we're talking about methane, right, so carbon is bonded to 4 hydrogens. Each hydrogen, right, has an unhybridized s orbital, and each hydrogen has 1 electron in that. So I'm going to go ahead and sketch that in. Let's go ahead and use blue here. All right, so here's an unhybridized s orbital. I'm going to go ahead and draw these in. So an unhybridized s orbital. Each one of these unhybridized s orbitals for hydrogen has 1 valence electron. So I'm going to go ahead and put in those 1 valence electrons in here like that. So same for here, and then finally for here. And so this is just one picture of the methane molecule. So this is hydrogen. Right, these are all the hydrogens right here like that. All right, let's think about this bond that we formed right here. So here we have an overlap of orbitals, right? An overlap of an sp3 hybrid orbital from carbon with an unhybridized s orbital from hydrogen here. And so this is a head-on overlap. Right, so we're sharing electrons here in this head-on overlap. And a head-on overlap in chemistry is called a sigma bond. Right, so this is a sigma bond here, a head-on overlap. And this happens 3 more times in the methane molecule, right? So here's a head-on overlap, here's a head-on overlap, and here's a head-on overlap. And so we have a total of 4 sigma bonds in the methane molecule. So a single bond here is represented, we're instead of saying a single bond now, we're saying it's also can be called a sigma bond, so this head-on overlap. Let's look at the ethane molecule now. So for ethane, we'll go ahead and draw that in. So ethane would be C2H6. Right, so we have 2 carbons. So let's go ahead and draw in those 2 carbons. And then 6 hydrogens. So we put in our 6 hydrogens around there like that. All right, when we're thinking about hybridization, we've just seen with methane that a carbon atom with 4 single bonds will be sp3 hybridized. Right, so I go back up to here, right, this carbon right here. Right, 4 single bonds, it's sp3 hybridized. We can use that same logic and apply it to ethane here. Each of the carbons in ethane has 4 single bonds. So each carbon in ethane is sp3 hybridized. So we can go ahead and put sp3 hybridized here. So let's go ahead and draw the picture with the orbitals. Right, so let's get some more room. If each carbon is sp3 hybridized, that means each carbon is going to have 4 sp3 hybrid orbitals. So I can go ahead and sketch in 1 carbon, right? Once again, I'm ignoring the back lobe, right? 1 carbon with 4 sp3 hybrid orbitals. And we know the other carbon is also sp3 hybridized, so I can sketch in 4 sp3 hybrid orbitals for this one too. So here's my 4 sp3 hybrid orbitals for this carbon. All right, in terms of electrons, let's go ahead and put in our electrons here. So this, let's see, there's 1 electron in this orbital, 1 electron in this orbital, 1 electron in this orbital, 1 electron from this carbon. And then for this other carbon, right, so there's 1 electron in this orbital, 1 electron in this orbital, 1 electron in this orbital, and 1 electron in this orbital. And then we can go ahead and put in our hydrogens, right? So we know each hydrogen has an unhybridized s orbital with 1 valence electron. So I can go ahead and do that and draw on the rest of our hydrogens. So that's 4 hydrogens, 5 hydrogens, and then 6 hydrogens like that. All right, we just said that a sigma bond is a head-on overlap of orbitals, right? So here we have a head-on overlap of orbitals, the bond between the 2 carbons, and then of course all of these are 2. So when we count all of those up, right, that's 4, 5, 6, and 7. So there are 7 sigma bonds in the ethane molecule. So 7 sigma bonds here. And we can go up here to this dot structure and look at them again, right? So here's 1, 2, 3, 4, 5, 6, and then 7. 7 sigma bonds. Let's focus in on the bond between the 2 carbons now. So this sigma bond right in here, right? So that's a sigma bond. And there's free rotation about this sigma bond. So if you can imagine rotating around this bond, so these carbons can rotate in space, and that's going to give different conformations. So you can have different conformations of the ethane molecule, which is in later videos. All right, so you have free rotation about sigma bonds. All right, let me go ahead and write that because that's pretty important. So free rotation about sigma bonds. And then the last thing I wanted to point out about the ethane molecule here is the bond length. All right, so the length between this carbon and this carbon. So this bond length in here turns out to be approximately 1.54 angstroms. So you'll see slightly different values in different textbooks, but we'll say it's approximately this value. And the reason we want to know that is we're going to compare this carbon-carbon bond length to the bond length in some other molecules in some later videos.